Okay, so on the previous video, we have looked at how can we determine the given vector field is a conservative vector field or not. So as I mentioned before, if the vector field given is a conservative vector field, there are some calculation, or there are some theorem can help you to simplify your work in calculating the line integral. Okay, so before we proceed with more complicated calculation, so I want to introduce you some theorem where this theorem is very helpful in simplify your work. Okay, especially for the conservative vector field. Okay, one of the theorem that very useful is fundamental theorem for line integral. Fundamental theorem is actually from the fundamental theorem of calculus, where we simply say the FTC, fundamental theorem of calculus, means that if you integrate the derivative of f respect to x, then you will get the fx back, and you have to replace the x equal to b minus the x equal to a. So that is the fundamental theorem of calculus. So for the line integral, because you can see here for the line integral we have a single integration, right? It will, after you do the f dot dr, you will have the single integration. So here we can use the fundamental theorem of calculus. So in this case we call it as a fundamental theorem for line integral. Okay. Okay, so meaning that, so if f is okay with the condition that, so there is a condition to apply this theorem. So the condition is the vector field given here must be conservative vector field. So first you have to show that the f here is conservative vector field using the curl f. So if your curl f is 0, then we can say that the given vector field is conservative vector field. And then and this vector field continuous on an open connected region. So open connected region. So what does that mean? Open connected region. So you have to look back the condition here. Okay, open and connected region. Okay, but that is a condition. So normally when the question for the exam 6, the function given is already in the open connected region. Okay, so if f is a conservative vector field and continuous on an open connected region, so the scalar potential function here exists, where we can say that the vector field f given is equal to the gradient of phi. Okay, and then if the curve C, because normally we evaluate the line integral along the curve C, right? So if the curve C is any smooth curve from A to B, so you have any smooth curve from the point A, so this is A, to the point B, so to the point B, lying entirely in the open connected region. Should be open. This is not closed. Okay, open connected region. So then we can apply the fundamental theorem for line integral. So in this case, we don't need to compute the f dot dr, but you can use the potential function, the scalar potential function that you obtain after you can test, or you can verify that the f is conservative vector field. Okay, which means that if you look at the question, the previous example, so once you said that the f is a conservative vector field, then you can obtain the phi. So in this case, the phi here is this function. So by using this function, so you just put here and substitute the middle point and substitute the initial point, and you can get directly the answer without evaluating the f dot dr and do the integration from A to B. So in this case, your work becomes simpler, right? Okay. Okay, so now how can we implement that? We can look at the example. Now I call this as example 8. Okay, so this one is example 8. Okay, so here we can see that. So okay, the vector field given is a force field. Okay, describing a force. So this is a force field. And the first question show that the force field given, the force field given is conservative vector field. So show that. So the curl F. So now we want to show that the curl F is 0. I, G, K, I, del X, del Y, del Z, del X, 2x, y, z, x squared z, x squared y plus 2z, 2x, y, z. Okay, so the first component, G cross K, will give you I. So, del y of this, so you can have x squared minus del z of this, so you have x squared. Okay, and then K cross I will give you G, so you have 2xy minus, so this del x of this, so this one 0, and you have 2xy, 2xy. And then I cross G will give you K, you got 2xz, so del x of this, so you got 2xz minus del y of this, so you got minus 2xz. And now we obtain that the curl is 0. Okay, so we can conclude that F is a conservative vector field. Okay, so now look at the B. Find the work done. Work done, what is the work done? So it is a line integral. So to get the work done, F dot TR along the curve C, and F is given. Okay, and then so now look at the curve. So the curve is, you have to read carefully the work done by the vector field given in moving an object along the line segment beginning. So you have a line segment in 3D from the 1, 1, 1 ending at 2 to 4. 2 to 4. Okay. So now if you use the previous step where first you have to find the f dot dr, and then you have to find the vector function of this line segment, and then you determine the t, and then you integrate. So that is the step, the regular step that we have done before. But in this case, we have a bit shorter step where we have shown on part A, F is conservative vector field. So in this case, we can write down, since it is a vector field, so we can obtain the scalar potential function phi. So now, instead of we do the same as the previous technique, which is sometimes is a bit complicated, it's not so complicated, but sometimes it be messy and need a longer steps. So now we work using the scalar potential function. So now and this one is equal to the phi x, the component y is phi y, and the component z is phi z. So now we can say that the phi x is equal to 2xyz, and phi y is equal to x squared z, and then phi z is equal to x squared y plus 2z. So when you just want to get the phi, you have to integrate, right? So your integration, then you will get the phi. So you have to integrate 2x, y, z dx. And this one, to get the phi, you have to integrate the function x squared z with respect to y. And the third one, phi x, y, z is the integration of x squared y plus 2z dz. Okay, so as I mentioned before, to get the scalar potential function, so we don't have the this one is indefinite integral. So meaning that when you do the integration, you will put the constant. So now firstly integrate with respect to x, so you have x squared yz plus a. This one with respect to y, so x squared yz plus b. And the third one integrate with respect to z, so x squared yz plus z squared plus c. So based on all the three result here, so we combine them, so to obtain the only one single scalar potential function, which means that if you see some of them, they are the same, right? So we just take one of them, so this one and this, the second one is the same, so we don't take. And this similarly for this, they are already the same, so just take this one. So now your scalar potential function is given by x squared yz plus z squared plus d. Okay, so in this case, you want to compute the work done given by f dot dr along the curve C. So because of the function here is a conservative vector field, so we managed to get the scalar potential function is does exist, which is given by this equation. So now by using the fundamental theorem of calculus, where we have a fundamental theorem of the line integral, so we can implement this where we have the open. You can see here it is, the condition here is open connected region. You must have an open curve. Okay, so this is open curve from the point of 1, 1, 1 to 2 to 4, 2 to 4. So using the fundamental theorem of line integral, so you have to substitute the terminal, the terminal. So in this case, we can rewrite. So the line integral from the point of 1, 1, 1 to the point of 2 to 4, 2 to 4. So using the fundamental of line integral, so phi, and we substitute the upper bound of phi 2 to 4 minus phi at point of 1, 1, 1. So we just evaluate the result that we obtain. We substitute the points of 2 to 4 inside here. Okay, so then you will get so you have 4, 2, and then 4. Okay, plus 4 square plus d. Okay, minus now phi at 1, 1, 1. So you have 1 plus 1 plus d. So 32 plus 16 plus d minus 2 minus d. So the constant will cancelling out. So you will get so when you evaluate that, so you got 32 plus 16 minus 2. So you got 46. So now you can see that our calculation to obtain the work done using the line integral is a bit simpler. So by using the function of the scalar potential. Okay, so first you have to show that the given vector field is conservative. Okay, so you have 2D ing only. So f is x y squared x squared y. So now find the curl f. So I have only ing. So del x del y x y square x square y, and then find the determinant. So obviously I cross j will give you only k and the rest is 0. So del x of x squared y will give you 2xy minus del y of xy squared also 2xy, and you will get 0 0 0. So we can conclude that the f given is a conservative vector field. Okay, so if you know that your vector field given is a conservative vector field, I'm very happy if I got this particular result, because I can simplify many work in order for us to evaluate the line integral here. Okay, so next you have to evaluate the line integral for A, B, and C. You have a different situation here, but the same vector function and the same problem. Okay, look at the case in A. Okay, so the case in A, you want to get the f dot dr where the curve is. So you have to read carefully. You have a line segment from 0, 0 to 1, 0, and you have the curve. Okay, basically you have the curve where it is given by y equal to the square root of 1 minus x squared. Okay, so then we should know what is the curve looks like for this particular equation, and then we need to rearrange. So y squared plus x squared equal to 1, so it looks like it is a circle, but your y is always positive. Circle with this one, 1 1 on y-x plane. Okay, so now we read again the instruction. So you have the line segment from 0, 0. 0, 0 is here, and then to 1, 0 along this line segment. Okay, so 0, 0, 0 to 1, 0 along the line segment, and then from 1, 0 to, okay, you have set 2 over 2. So set 2 over 2 meaning that it looks like xy is the same, so it should be at this point, I suppose. So that one is the point of set 2 over 2 set 2 over 2. Okay, so from 1, 0 to set 2 over 2 to set 2 over 2 along the circle, and then and the line segment from the set 2 over 2 to 0, 0. So you have this one. So you got 3 curves there, C1, C2, then C3. Okay, so meaning that in this case we have to erase this. Okay, and also this one. Okay, that is only your curve, right? Segment, 2 segment lines, and part of the circle with this one. Okay, so then you need to obtain the f dot dr. So since we already obtained that f is a conservative vector field, so it looks like we have a closed curve here, right? So closed curve or closed loop, because from 0 0 and then it back to the 0 0. So in this case we have a closed loop, and since f is a conservative vector field, and we can just say that your f dot dr is 0. Okay, just simple. Use the property of closed loop property. Okay, closed loop property. Okay, remember I just jot down for if you manage to obtain that the f is a conservative vector field, you have to apply the fundamental theorem of calculus. Number 2, you have the path independent, and then the third one, closed loop property. Okay, what else? Closed loop property, path independent, and fundamental theorem. So only 3. So this one is only applicable if your f is a conservative vector field. Okay, so now based on the question A here, since it is a closed loop, then we can apply the closed loop property since f is a conservative vector field. Okay, so now the next C here is also part of the circle with radius 1 on y-axis plane. Also based on the equation of y squared plus x squared equal to 1. Is the curve. So it's the curve from 1 0. So the point here 1 0 is here, and then to the point of SSCE2 over 2 to SSCE2 over 2. So you have an open curve. Okay, only that one. So in this case, I have to erase this one. So this is not part of the curve. So only this. Okay, so it looks like since f is conservative vector field, we can apply the fundamental theorem for line integral or fundamental theorem of calculus. So we want to get the line integral f dot dr over the curve that we obtain here. Okay, no, that curve. So now we want to apply the let's say here I give a name. So the initial point is A and the terminal point is B. So A is at the point of 1 0 and B is at the point of SSCE2 over 2 to SSCE2 over 2. Okay, so now f dot dr from A to B. So we need to find out the scalar potential function and put B minus scalar potential function and substitute the point A. But in this case, you need to find out the scalar potential function. So as we know that since in this case f is a conservative vector field, then we can write down in that form where we can have phi x is equal to, so what is the f component? Okay, only 2 x and y, so xy square, and phi y is x square y. So then phi xy, you will integrate xy square with respect to x, and for this one you have to integrate with respect to y, x square y dy. Then this will give you 1 over 2 x squared y square plus a And the second one will give you 1 over 2 x squared y squared plus b. So when you combine them all together, so you have only 1 over 2 x squared y squared plus c. Okay, you have only 2 integrations here because your component is only 2 ing. Okay, so then this is the phi, so we substitute the phi at the point b is, what is b? B is sec 2 over 2, sec 2 over 2, sec 2 over 2. So 1 over 2, 2 over 4, and 2 over 4 plus c. So we will get this one cancel, this one 2. So 1 over 8 plus c. And then your phi a, so this is phi b, and then phi a is phi at the point a is the initial 1 0, then substitute, so you will get 0 plus c, so you got c. And then when you have phi b minus phi a, then 1 over 8 plus c minus c, and you will get 1 over 8. So this one is your line integral along the c from the fundamental theorem of calculus. So your result here is 1 over 8 using the fundamental theorem of calculus. Remember, to obtain that, you must have an open curve. Okay, so we done B, and you can see that the calculation is a bit simpler. So now we go to the C. So what is the C? C, you need to get the line integral f dot dr. Now I want to see what is the C that we have. We have a line segment. Okay. From 1 0. Okay, so actually you want to go to from 1 0 so let's say this is 1 0, and this one is sec 2 over 2, sec 2 over 2. So you have to read the instruction carefully. Line segment from 1 0 to 1. So this is 1 and this is sec 2. So this one is the point of 1 sec 2 over 2. Okay, so in this case you have the curve. So you want to go to 1 0 to sec 2 over 2 to sec 2 over 2. But then you passing through the 1 sec 2 over 2 first. Okay, when I read again, from 1 0 to 1 sec 2 over 2, we have a line segment. And then another line segment from 1 sec 2 over 2 to sec 2 over 2, sec 2 over 2. So this is another line segment. So you got C1 and C2, both are line segment. Okay, but actually your initial and terminal is similar to the curve in B. Okay, so if you compare your B, you want to go 1 0, the point of 1 0 to sec 2 over 2, sec 2 over 2, isn't it? Similar to the C. But for B, you go direct along the circle. But this one, you want to go to the C. The initial and the terminal is the same, but you have you are passing through the two curves here. And since your initial and terminal is the same as in B, and your F is conservative vector field, then we can apply the path independent property. So based on path independent property, so the F dot dr for the curve in C here is also the same as in the result of B in B. Okay, so without any calculation, and we can directly find out the value. Okay, but in this case, I give you, if you look at the, actually the answer is given, but if you look at the result in B, so from 1, 0 to this point, this step is using the standard calculation where you have to find the vector function of this, and meaning that you have to find the parametric equation of the circle where the x is cos theta and the y is sin theta, and then you have to find the specific angle using the point that you have obtained, that you are given here. So in this case, based on the point given, so the theta is 0 to pi over 4, and you have to find the f dot dr and do the integration and so on, and the answer will be the same. But as I mentioned before, since the f is a conservative vector field, then we can apply the fundamental theorem for line integral or fundamental theorem of calculus, and the answer is also 108. But for me, this one is more simpler, but still okay to be done in this form. So it is up to you, because they don't mention using the some specific property. So you have an option to choose any method as long as it is makes sense. Okay.